Hello friends, welcome back to another video on this channel. In this video I will show you how I made this sun tracking solar panel using a Arduino Uno as well as two LIDAR sensors along with a servo to control the movement of the solar panel. First of all, let me show you how it works. So here, as you can see, I have a regular smartphone with a torch with the flashlight turned on. This is because even though this is intended to be used with the sun in outdoors, of course the sun doesn't exactly work the way I want it to, so it won't exactly be as fast. And so in order to show it on video, I'm using a normal cell phone light because this is the best way to show it. However, of course, if this is in the sun, this works in the same way. So as you can see here, I am taking my cell phone and I will put it on top. So as you can see, as I move it, the solar panel will move along with the along with the movement of the torch. The solar panel moves in order to keep the light in the focus, but basically it's trying to keep the light as much as possible on the solar panel so that the ray of the sun falls on the solar panel in order to achieve the maximum amount of energy possible. Now of course this is a small scale demo. This is just a proof of concept, so this is not exactly a very large solar panel, as you can very clearly see, nor is it very reliable. As you just saw, just with a little bit of switch in lights, it starts flickering around and starts it doesn't work that well, because again, as I said, this is a proof of concept, and of course the distance between the two LIDAR sensors, or photoreceptors rather, are actually very short. So really the amount of movement the light has to do is very short, so it really is easy to for itself to mess itself up. But as you can see, as a neat proof of concept, it does work, and it works quite well as a proof of concept. As you can see, as I move the phone around, the solar panel moves. You can see it better on the top view camera. So yeah, it really does show how engineering can help simple problems. As you know, most of the time solar panels are fixed. However, this helps in that by helps in increasing the amount of energy that the solar panel can achieve, because it's getting more sun throughout the day instead of just getting it to one time of the day. With that being said, let me show you how this works. So first of all, I will disconnect the barrel jack, which is the way I'm plugging it in. This is because even though the Arduino can very well power up the servo itself using the USB plug, it is a bit jittery and not that reliable, so I'm using the barrel plug. I'm currently supplying it with 9 volts for this. So as you can see, it's really a simple mechanism. I have two LIDARs connected down into the breadboard, which is going through a resistor. As you can see, there are two resistors which are plugging it into ground. I also have a servo which is plugged into the Arduino. Now I'll leave the detailed circuit diagram down in the description along with the code. As you can see, it's up on the screen. Now along with the servo, as you can see, I have this little red this is just a paper clip that I bent up in order to make it work for this. So as you can see, it's on a little this solid syringe like thing, and then I have it a straw mounted onto it, and then I just have the solar panel hot glued onto the straw. Now as you can see, the solar panel isn't really connected to anything. As you can see, just two wires coming off of it, because again, as I said, this is just a proof of concept, and it really is not very it's not very usable. This solar panel only produces about 5 volts of current at only a half a watt, so it's really not that much amperage. Even to charge a normal smartphone, it will take really a long amount of time, so it's not very usable. And of course, for this small amount of solar panel, it's not really needed. And of course, for this amount of power, it's not really needed for a system like this to have it tracking the sun. This is just again proof of concept. But anyways, I will have the circuit diagram in the description along with the code. So let me just show you a bit on how the code works. So I will switch over to the computer video screen recording now. Alright, so as you can see, I have now switched over to the computer. So this is the code that is running on the microcontroller. It really is very simple. So first of all, here we are just defining the servos and the pins and all the things. Now this is one important thing you should know. So this is the error. So of course this is again very hobby based and not very reliable, as I mentioned before. So there is quite a noticeable amount of error between the two LIDARs. So in order to prevent it juttering, like you saw in the beginning of the video, you should set this error to something that works. So I set it to 20 because that seems to be working good enough. It's accurate, but it still prevents quite a lot of that jittering. you can set it based on your lidars and what you are using. It really depends on different lidars, how and the like the error amount you have to set. If you are using like a nice high-end lidar sensor or photoreceptors rather, it's not needed to be this high, whereas if you are using like the cheap, like the ones I am using, this is should be quite a high, like 20. Even if you are using maybe some more like different lidars, they may be even higher or lower. That you have to do just a little bit of experimentation. I'll talk more about this just in a bit. Next up, we are just setting the servo to 90 degrees. So this is just a middle of 90 degree. The servos move 180 degrees, so this is the 90 like the middle of where it is. This is usually where you want it to be. So it's, you can set the like the basically the connection to the servo and the solar panel, so it's roughly flat. So when you can change the next settings, you can have it be like where you need it to be. Next up, here we are just starting the serial and attaching the servo to pin number 9. Next is, here is where the really the main part of this, the calculation starts. So this entire part really till here. So first of all, we are just telling it that the integer east LDR is to read analog pin east LIDAR pin, and same for the west. Then here we are saying if both of these are less than 40. So the way this works is basically the LIDARs change the amount of resistance based on the amount of current. Now they are inversely proportional, so the more the current, the more the more the light, the more resistance they will apply. So it's basically that is what is the Arduino is measuring. So it's connected to ground and 5 volts, and the Arduino measures the amount of resistance provided by it by seeing the amount of current, and based on that it can tell how much light is there. So if it is less than 40 on both, then it will consider it as low light and it will put it towards the east for sunrise. Then next, here we are calculating whether it is, then we are calculating that where exactly the servo is. So if both of those are high, one of them are greater than 40, it will then do this. So it will first see the difference between the east and west lidar. If the east lidar is greater than the west lidar, that is, there is more sun towards the east than the west, it will then set the servo to move the solar panel towards the east by moving the pin downwards. As you can see in my setup, the way it is working is the servo, when it moves the pin downwards, the solar panel comes towards the east, and when the when the servo horn moves upwards, the solar panel goes towards the west. So I have it set to go to 10 degrees of the servo to move it towards the west. And then next, we are, if the east lidar is less than the west lidar, that is more sun towards the west, then the servo will write 150 to go towards the west. Now again, this is not like, it does not change where the servo is, the solar panel is, depending upon the time of the day. It just has two sets. So as soon as the sun is more towards the west, it will move towards the west and stay there, and if it is more towards the east, it will stay towards the east. It is not like, it doesn't change its position every so often to keep it exactly down the sun. This is again because of the fact that this is like hobby and all those reasons I told you before. So that's the reason this is not exactly the most efficient way to do it. If someone were to implement this in a real life situation, I would highly recommend them using higher quality photoreceptors, and so they can have like the accurate control over it, so they can change the change the position of the solar panel every so often to keep it exactly under the sun. Unlike here, it's just on two sets, so it, when it's on this side, it will move directly to that side. Now it's mostly still going to be not that less efficient, it's far more efficient than just having it still, but still this is there is some more tuning to be done. Now this here, down here, this is where the debugging starts. So this is, it will put the values of the east lidar, west lidar, as well as the where the servos is set. Now this servo set is not very accurate, there's some problems with this, so it doesn't update that this integer very much. It just keeps it where it is at 90, which is where it starts off. So this is not really accurate, but other than this, all these values are extremely important, so you can see whether or not your system is working. You can, even without having the servo connected, you can see whether the resistance is going up and down by just having a flashlight like I did and moving it around and checking out the serial panel, serial monitor. So it's really a simple little device and quite a simple sketch for this, as well as the code is not that big, and it's really not that complicated to understand either. So this is something I highly recommend some beginners to do. So yeah, if you like this video, please subscribe to the channel and leave a like, and you can comment anytime about future ideas, as well as if you have any problems with this video. So I hope you guys enjoyed, and I'll see you guys next time. Bye.